Today's topic is frictional losses in grain. Basically, what we are interested is in determining the system curve when the airflow rate goes into the grain bin. How does the frictional losses in the grain changes? That's what we are interested. Okay. Before we get started, let's review, stop back and think about what we have done so far. We spent quite a bit of time last week learning how to collect a fan curve. We went to the lab, understood how the fan is set up connected to a long pipe. We use a pitot tube to measure the static total and the velocity pressures and plotted a fan curve. We also learned to interpret the fan curve. Where are the stable and the unstable regions in the fan curve are? And we looked at fan loss, how does it changes? And we also looked at the multiple fans. How does the fan performance curve changes? And earlier this week, we learned about the moisture content of the grain and its relationship with the relative humidity of the air, which is the equilibrium relative humidity and the equilibrium moisture content and an isotherm. So that's basically the water activity, which is nothing but the ERH divided by 100. And we had a EMC. There exists a relationship, and that relationship with the changes with the temperature, right? So we also looked at that. We also spent quite a decent amount of time looking at the psychrometrics of air, which is the psychrometric chart, how the properties changes when the air moves through the drying bin. It follows the constant enthalpy line or the wet bulb line. And we learned the system curves of the simple piping system and operating points. So now to connect all the pictures, now we are going to learn the system curve for a grain bin. Once we know that we can connect all the pieces, we can determine how long you need to operate a fan to dry the grain from a given moisture to the safe moisture content. So we can determine that. So let's think through. How did you determine the system curves in the pipes? So we had the Fanning's equation, the F major or the F in the pipe is equal to 2 into F into L by D into V square by 2G. And then we had the F minor, which is about sigma CF into V square by 2G. We need to make sure the units are correct, and then we need to add it in. And then we had basically plotting Q versus the total F total, right? So that's how we did it. So this one is Darcy or the Fannings came up with this equation, and these are empirical formulas. So for a simple pipe system, we learned how to determine a system curve. So how would we determine a system curve for a complex system? We did do it on selection of a pump for a non-Newtonian fluid where heat exchanges and others were there, but we considered that as a pipe too, and we simply did it. Let's say you have a complex system. There is no relationship out there. How would you do it? The one way to do it is, so let's say you have a system and you have a pump or a fan. So I'm trying to get my pen working again. It's not working again. I hope it can make it work. Come on. Okay, I think it's working now. Okay, so let's say you have a system, unknown system. It's a complex system, right? So it can have a bunch of things. Let's say like an evaporator, a distillation column, and so on. Let's call it, as for an example, a distillation column or something, right? It's a complex system. You cannot simply do it by the thing. So let's say I have like a pump, and then I have things going on. So how would I know how would I develop a system curve for this? So if I put a pressure gauge, here, and if I put another pressure gauge here, if this is P1 and if this is P2, then the pressure drop, the frictional through the system, is P2 minus P1 at that Q, right? At that flow rate. Then you change the Q, right? You keep changing the Q and find out how the system looks like. So that's how you would do it. Same thing if you want to do the grain bin. So you can have a grain bin filled with a grain, and you can have a fan, and if I know what's the pressure gauge here, and here I know that it's atmospheric pressure when it comes out. So if I measure this pressure and if I know what is the flow rate, I can estimate what is the frictional drop in the grain bed. And it's interesting that the University of Nebraska pioneered research in determining airflow resistance in grains as early as in mid-1950s. So, because corn is a major crop and we had a major research university here, and then we pioneered the research in this area. So, I want you to be aware of that. It's a historical thing, but we pioneered in the world. So, that's what we are going to learn today. So pressure drop due to airflow in the grain. We talked about the airflow. Airflow is an energy-driven phenomenon. A grain bin, basically the way the grain bin works is, you basically have a perforated floor like a screen over which you are going to fill the grain. And at the bottom we call this as a plenum chamber, or the air chamber, and basically you are going to connect a fan, and the fan is going to build a pressure, and then it's going to go through the grain bin, right? There is a ductwork there, and there might be some elbows, there is a perforated floor, there is a grain, and all of those things are there, okay? So basically you need to size the fan to have a desired airflow rate through the grain bin. Again, it's the basic generic stuff. When air is going through the grain bin, it's basically going through the porosity, right? Between the particles there are spaces through which the air is going through. If the air is drier, whose relative humidity is lower than the moisture content, equilibrium moisture content of the grain, because of the non-equilibrium, the air will start picking up the moisture from the grain, and it will move out. You will dry the grain, right? So here is an example. So you have a grain bin, you have a fan. Here is an example of an axial fan. So here is a plenum chamber. So if I connect a U-tube manometer, I see about 2 inches of water pressure. When the air comes out, if I connect it, because it's exposed to atmosphere, there is 0 inches of water. So the total pressure drop is equal to 2 inches of water at a certain flow rate Q1, right? So that is a Q versus the F of grain. That gives me one of the points. So similarly, if I get multiple points, so if I can change the speed of the fan, I will get a system curve of the grain bed. And if the grain depth is changing, let's say we are unloading some grain and sold some grain, and the system curve is going to change, right? or if I change the grain, it is going to change too. So the pressure drop is primarily related to the flow rate. That's the system curve, right? Q versus the F. F is nothing but the pressure drop, right? And the broken grain versus the foreign material, do you have a clean grain? Or do you have a grain that has been handled several times that you have a lot of powders in the grain, right? And that's going to increase a lot of resistance. The packing factor, some of these grains are stored for a year or two. And some of these, so basically you have a silos. Those are the concrete silos about almost like 100 feet high, which you see in like in 27th and north of Cornhusker, or on the side of the Cornhusker Bridge. So you see these large concrete silos. And you have also the metal bins, right? Metal bins and concrete silos. So you can see that because of the mass, it can pack and it can change the resistance to airflow. Of course, the type of the grain, whether you have a corn or a soybean or a wheat, the resistance is going to change, or the rice, it's going to change. The depth of the grain, whether it is filled completely or halfway through, is going to affect, and the amount of fines, the amount of dust. So for example, the clean corn, compared to clean corn, the 30 to 40% fine doubles the pressure. Okay. So what they did is, they generated, instead of like a fanning equation, they typically initially generated these graphs experimentally. So what they typically do it in the lab is that like they take like these barrel containers as a model bin, and then they connect it to a fan, and then they fill the grain to a certain level, and they connect a pitot tube with a multiple depth and measures the pressure drop. The one key thing you want to understand is in the mid-1900s or 1950s, when Nebraska and other universities developed it, they flipped the graph axis. So they put the Q on the y-axis, which is actually the CFM, feet cube per minute, per the cross-sectional area, so which is basically actually the velocity actually, right? Feet per minute. They put it on the y-axis, and then they put it on the x-axis, the pressure drop per unit depth of the grain. So in a grain bin, if it is stored at 10 feet, you divide the total pressure drop divided by 10 feet. So what they found out is the depth is linearly related to the pressure drop. So they normalized by that, so inches of water per feet. And then they had these logarithmic axis. And then they generated almost like a linear curve on the log axis. So here is the wheat. So this is how it looks like. So if my velocity is, let's say 2 feet per minute, then the pressure drop is going to be about 0.015 inches of water per feet of grain. And if my grain bin is 100 feet high, then you multiply by the 100, and so many inches of water pressure drop it's going to occur in a shelled corn. If it is wheat, because it's a finer grain, it's going to offer a lot more resistance. It's going to offer a lot more resistance, and the values are going to look 0.04 per inches per feet. Okay, so these are typically called as a shed curve, because there was a faculty member named Shed who was working at the University of Nebraska, determined a lot of these data in his period, because he was the pioneer in doing it. These curves are known as the shed curve. So earlier when we saw it in the English units, they also do it on the SI units, which is the meter cube over A, where A is the cross-sectional area of the bin, so which is basically meter per second, and also the pressure drop per unit depth, they will get it in pascals per meter. So the same graph, they explained it in SI units. So there is a ASABE standard posted on the blackboard. You need to look for it, and you need to have these charts available to determine these things. And they did it for a variety of the things, like a bell pepper, sweet potatoes. You know, when I went to visited a French fry processing plant, they were storing potatoes on these long, big storage bins, and they can control the necessary humidity and the conditions such that they can store the potatoes for a long, long time, almost 6 months to a year. Whereas one time when I was in India, the capital New Delhi, I was hearing the news that the potato harvest was so high, and they didn't have a good storage conditions like we do have here in US, and the prices dropped to like pretty low, few pennies a kilo, and the farmers felt that like it's not even worth their money to transport it to the market, and then they were throwing it in the field. Okay, so the storage of grains and the products is very important. If you think about it, in US, we lose about like a 5 to 10% of the grain due to losses, storage losses. In Africa and developing countries, it's almost like 30-40%. Fruits and vegetables more than half. So we are basically losing all these products just for the waste. If we can save that, a penny saved is a penny earned, you basically increase the food availability. You can reduce the food hunger, reduce the food prices, right? So these storage and the designing the fence is very important to make an impact in this world. And even when you look it up here in Nebraska, our grain storage structure is so efficient that you can take a grain and burn it and use it as a fuel. It is very efficient because we store the grain so efficiently, right? So we do need to learn all of these processes. So here is the peanut and shell, and of course, as you move ahead, the grains are offering more resistance. So the rice is going to give you a lot more resistance than a bell pepper, which is much bigger, and then you have a lot more space around it. Potatoes are going to offer much less resistance compared to the sunflower seeds. And of course, the moisture content of the grain affects too. They are given in wet basis. I hope you remember what is a wet basis. It is the amount of water divided by the total wet weight. That's going to affect. So if you have a higher moisture content, the grains are going to a little bit swell, right? And it's going to reduce the porosity. When it reduces the porosity, it's going to increase the air resistance. So they have like a bunch of different graphs. So here you have corn with a whole ear, and different beans, and the shelled corn, and the wheat, and the alfalfa. So you can see that these are important for the food and the feed industry, for storing them efficiently for a long time. So the shed curve, commonly known as, they are data driven. So you measure it in the lab and you plot the graph, right? And you need to consider the effect of graining, because in the lab you do it with a clean grain, right? Whereas in real life, it's stored about 100 feet high. Therefore, you do need to have a good consider the packing factor. Typically, you multiply by 1.5. We call it as a packing factor. So you multiply by 1.5, whatever the values you get to accommodate for the packing. Use of spreaders, so if you have augers and other stuff that can affect, and if you have like a significantly lot more fines, you want to consider when you are selecting stuff. And also the floors and the ducts. The floor is like a sieve kind of stuff, a perforated floor. So in a bin, at the bottom, so if you look at this one, right? If you look at this one, so it has a lot of perforations. Okay. The grain is stored over it and the air is pushed through the perforated floor. And people showed that the airflow resistance of the bin floor is pretty low if the open area is greater than 10% or so. Okay. And because the most commercial available floors are greater than 10% open area, the resistance offered by the floor is pretty low. There is also the air supply duct, tunnel, and a lot of those things offer some resistance too. And what in the practical field people figured out is, instead of trying to determine the frictional pressure drop in the duct and the elbows and the turn and all of those things, for most general typical conditions we find in US, you can just estimate about a half an inch of water pressure drop for all of these things together. And then you determine the frictional pressure drop due to the grain and call it good. So the frictional total can be equal to half an inch plus the F of the grain for most conditions. Unless you have a specialty conditions where you have an extremely long duct, then you do need to consider that. But for most conditions, this should be good enough, and this can be assumed for your exams unless it's specifically stated otherwise. So here is an example of a graph. So as the percent sheet opening of the perforated floor increases, the pressure drops. So at around 10%, it's pretty low, that you can basically estimate along with the ducts as a half an inch of water and call it good and move on. So let's do some examples. What static pressure of a fan, okay, if you want you can say of a fan, is needed to deliver 1 CFM per bushel. This is another thing we need to understand. A bushel is a unit for volume that's commonly used in the industry. 1 bushel is 1.25 cubic feet. Okay, you gotta remember that. Okay. And also people call it as the density or the test weight. A test weight is commonly called. The test weight of the, for example, corn is like a 56 pounds per bushel. That's kind of like a kilogram per meter cube, right? It's kind of like a density. It's a density basically. So this is a bulk density. If you remember the difference between the bulk density and the particle density, a particle density is a density of a single particle like a grain, a single grain kernel. Whereas a bulk density is a density of the whole material grain in bulk, which incorporates the porosity and the airspace in it. So typically that is also a quality factor of the grain. So if the grain is infested with the grains and other stuff, you have the holes on the grain, the density is going to be, the test weight is going to be lower, and it will be graded a lower grade. The USDA has a grades of the grain, and they are all taken into factor. So typically the general requirement for drying, the recommended airflow rate is 1 CFM per bushel. Okay, typically. For aeration, the difference between the drying and the aeration is that the aeration is mainly for adjusting the temperatures in the grain. So you make the grain to be uniform temperature. You don't want a hot spot and a cold spot inside a grain bin. It's amazing that some of these hot spot temperatures can go so high that a grain bin can catch a fire. We can talk more about it in the class. For aeration, the recommended airflow rate is typically 0.1 to 0.4 CFM per bushel. So if I have a bin of volume of, let's say, 1,000 bushel bin, then I need to have a flow rate of 1,000 CFM, because multiplied by a 1 CFM for dry. And let's say I have stored on the grain bin 20 feet deep. Okay, so this is a shelled corn. 1 CFM per bushels, I convert it to the feet cube. 1 bushel divided by 1 cubic 1.25 feet cube. And I multiply by the 20 feet deep, I get 16 CFM per feet square, which is nothing but almost the airflow velocity. This is basically the flow rate divided by the cross-sectional area. And you can enter it in the chart. So you go to the shed curve. So these are the ASABE standards posted on the website. So you go to the airflow rate CFM per bushel, you go to 16, and pay attention that it's a log scale, so you need to pay attention to that. You draw a line and you hit shell corn and you come down, you get an answer 0.14 inches of water per feet. So the results from the chart data is 0.14 inches of water per feet of grain. You multiply by the 20 feet, which is the depth of the grain. You multiply by the 1.5, which is the packing factor, because this chart was for the clean grain. So that packing factor to accommodate packing. So you get 4.2 inches of water. So basically your fan should be able to supply 4.2 inches of water, and whatever the volume of the grain bin, let's say if it is a 1,000 bushel bin, then you need a flow rate of, if it is 1,000 bushel bin, then Q is equal to 1 CFM per bushel times 1,000 bushels equal to 1,000 CFM. So basically you need a fan that can provide you a flow rate of 1,000 CFM at 4.2 inches of static pressure. Then hopefully that one should work for your requirement. Again, it's important to generate a system curve and you superimpose over a fan curve, and you determine the operating point to make sure it provides the desired airflow rate, which is 1,000 CFM. Okay. So here is another example. What static pressure is needed to deliver 1 CFM per bushel through a 20 feet deep of milo or a grain sorghum? Okay. Again, you go through the same steps because it's the same thing. So I get the same answer, 16 CFM per feet square. So now instead of I go to the corn, I go to the milo, which is a finer grain. So it's going to offer a lot more resistance. and basically 0.32 inches of water per feet of grain multiplied by the 20 feet times 1.5. So it is going to offer a much higher resistance compared to the corn, because the milo, the type of the grain, is going to affect it. So you can see between the shelled corn and the milo, the static pressure increased from 4.2 to 9.6. So the pressure requirement is much higher. You can also use the chart the other way around. This is the way typically done to quickly estimate the airflow rate. Let's say I go to the middle of a cornfield and there is a grain bin there, right? I have a grain bin there, and then it's connected to the fan, and there is a certain amount of the grain in there. So I know what is its volume, so how many bushels, right? I know the value. Okay, let's say I know the value, and I know the depth of the grain, or meters or the feet. I know the value, and I want to determine what is Q. To determine the flow rate, it's a bit hard. You need to have a pitot tube. You need to traverse through, but actually here there is a disturbance. It doesn't work very well. And trying to measure the velocity there, it is a challenge. You can measure it, but there is a disturbance, so you don't get a good value. The most easiest way to do it on the field to determine the flow rate is to put a U-tube manometer, which is pretty simple. You get just a U-tube and fill it with the water and measure what is the pressure over there, right? Then if I know the pressure and if I know the depth of the grain, then I can go by and I know the type of the grain, and if I have a shed curve, I can estimate the flow rate in a reasonably accurate manner. So these are the steps I do. So I put a manometer, I got a value of 4 inches of water. So you have to go backwards. I need to divide it by the packing factor to make it for a clean grain. And I need to divide it by the grain depth to make it per unit depth. I get 0.18 inches of water. Then I go back to the chart, right? I go back to the chart, go to somewhere 0.18, and then I go up, right? And go to whatever the desired grain is. I'm not sure what whatever grain was. And then you determine what that value is. Okay. So that is around 20 CF. That is around 20 CFM per feet square. Okay. And then if I multiply by 1.25 feet cube per bushel, and also I multiply by the depth of the grain 15 feet. There is a typo in here. I should fix it. No, I need to divide it by 1 over 15 feet. So the units cancels out. Then the value is going to be, the answer is correct. Then my flow rate is 1.67 CFM per bushel. And if I know the volume of the grain, if I multiply by the bushel, and that is the flow rate, I can estimate what the flow rate is. Okay. So Q is equal to 1.67 CFM per bushel times whatever the volume of the grain bed. Then that will give me the flow rate. This is the way you can determine the flow rate in a grain bed. Like the fanning equation, so people also fit these data to an equation like a delta P by L, where delta P is the pressure drop in Pascal or inches of water, divided by L. The L is nothing but the bed depth, and which is equal to 8 times, pay attention here, Q Q is actually meter cube per second per meter square. So it's actually the velocity, okay? Q is actually the velocity. The units are meter cube per second divided by meter square, which is the meter per second. Pay attention, don't put the meter cube per second. Pay attention, this is the natural log. And they determine what the values of the A and the B, and they put it in. So here is the one, the table one. It's on the ASAB standard for a different type of the material. So you have the A in English SI units, B in SI units. These data were collected for these ranges of the flow rate by these people, Shed in 1953. You can see Shed. He did so many of these in Nebraska so long ago. Okay, and I also know few of the people on this list. JS was my master's advisor in Canada. And here is Jones. This is David Jones. He is the Associate Dean for College of Engineering here in Nebraska right now. So in 1992, he collected for some milkweed pots too. Some of you might be taking the heat and mass transfer class with him. Maybe you can go and then ask him about this. We can do this problem in the class. And basically that completes this topic. Again, to summarize what we have learned so far is the system curve for the grain bin. The key thing is to determine the F of the grain, the F total is equal to ½ an inch plus the F of the grain. The F of the grain is determined using a Shed curve or the equation. The Shed curve is a flipped curve. The axes are flipped. They have the Q over area, the CFM per feet square on the y-axis, and the pressure drop per unit depth or inches of water per feet of the grain, and then they have the value. Okay, from that from the curves you pick up the value. Remember to multiply by the packing factor 1.5, right? And remember to add 0.5 and you can generate a whole system curve. Okay, we can do this problem in the class. So let's conclude this video lecture now.